Hello and welcome to this video for OCR A-Level Physics in the module of forces of motion in the topic Newton's laws of momentum and on the concept of Newton's first and second laws. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe Newton's first law of motion, define and describe Newton's second law of motion, and calculate values based on Newton's second law of motion. So in this lesson we're going to look at the following parts of the OCR A-Level Physics specification, in particular Newton's three laws of motion. Now Isaac Newton looked at how we can explain how an object moves in terms of forces which change its motion. So one key idea of physics is Newton's laws of motion. Now these were the laws which everyday objects obey, and they determine the motion of these objects. Now they were published by Sir Isaac Newton in 1687 in his book De Principia Mathematica, The Principles of Mathematics. Now this book is actually a trilogy, and actually book 1 concerns Newton's laws of motion. Now these laws explain all motion in the everyday universe. There are no exceptions to Newton's laws. Now they are the most important laws of the everyday universe. So Isaac Newton looked at how he could explain the object moves in terms of forces, which we now call dynamics. So this resulted in Newton's laws of motion, which can describe the relationships between forces acting on an object and its motion. Now, the importance of Newton's laws of motion lies in their ability to explain a wide range of different phenomena, from the motion of planets to the behaviour of subatomic particles. Now, by understanding these laws, we can predict and explain the behaviour of objects in motion, allowing us to design and engineer systems that work effectively and safely. Now together, Newton's laws of motion provide a framework for understanding the fundamental principles of motion and force, which underlie many areas of science and engineering. They form the basis for classical mechanics, the study of motion of objects under the influence of forces, and are therefore a cornerstone of modern physics. Now their significance can be seen in many everyday applications, from the design of bridges and buildings to the development of space exploration technologies. Now in the 17th century, astronomers began to use telescopes to observe the night sky, and they saw objects such as planets could move freely through space. They simply kept on moving without anything providing a force to push them. Now Galileo came to the conclusion that this was the natural motion of objects. So it was considered that an object at rest will stay at rest unless a force causes it to start moving. A moving object will continue to move at a steady speed in a straight line unless a force acts on it. So objects move with a constant velocity unless a resultant force acts on them. Now being stationary is actually just a particular case of this, where our velocity is equal to 0. Now the tendency of a moving object to carry on moving is known as inertia. So an object with a large mass is difficult to stop moving. Think about catching a cricket ball compared to a tennis ball. Similarly, a stationary object with a large mass is difficult to start moving. So think about pushing a car to get it started. Now it's difficult to make a massive object change direction. So think about the way a fully laden supermarket trolley tries to keep moving in a straight line. Now all these examples suggest another way to think about an object's mass. It's a measure of its inertia, how difficult it is to change the object's motion. So uniform motion is the natural state of motion of an object. So when we say uniform motion, we mean moving with a constant velocity or moving at a steady speed in a straight line. Now, inertia is an everyday experience we encounter in all our lives. For example, a passenger in a car feels like they're being pushed backwards when the car accelerates forwards. This is because the passenger's body has inertia and resists the change in the motion of the car. When you try to push a heavy box, it may be difficult to get it moving because there's a large amount of inertia. When a football is kicked, it moves forward in a straight line until it's acted upon by an external force, such as friction from the ground. When a roller coaster goes over a hill, the riders tend to lift out their seats because their bodies want to keep moving in a straight line whilst the roller coaster changes direction. So when you turn a corner in a car, you may feel like you're being pushed to the side. That's because your body wants to keep moving in a straight line whilst the car changes direction. Now we are aware that if an object has a high mass, it has a high inertia. If it has a low mass, it has a low inertia. Now this leads to Newton's first law of motion. An object will remain at rest or in a state of uniform motion unless acted upon by a resultant force. This means that a body will stand still or move in a straight line at a constant speed unless there is a resultant force acting on it. So if the forces acting on a body are not balanced, the overall resultant force will make the body accelerate. So this could be a change in the object's speed, the direction, or both. Now, a resultant force is an overall force on an object. The resultant force is our observed force acting on an object. So the resultant force can replace the other forces in a diagram. So the number of forces acting on an object can be replaced by a single force that has the same effect as all the original forces acting together. Now, we should be aware that objects accelerate in the same direction as the resultant force that acts upon it. So if a resultant force acts on a stationary object, it will cause the object to accelerate in that direction. If the resultant force acts in the same direction of motion as a moving object, it will cause the object to accelerate in that direction by increasing its speed. If the resultant force acts in the opposite direction of motion for a moving object, it will cause the object to accelerate in that direction by decreasing its speed. And if a resultant force acts in a perpendicular direction of motion as a moving object, it will cause the object to accelerate by changing its direction of motion, but not its speed. Now, Newton's second law of motion says that the acceleration of an object is proportional to the resultant force acting upon it. This can be written as the equation F equals ma, where F is the resultant force, m is the inertial mass, and a is the acceleration. This indicates that the greater the resultant force acting on an inertial mass, the more acceleration that you will get. It indicates that for a given resultant force, the more inertial mass you have, the less acceleration you get, which indicates that mass is an inertial mass as it provides a tendency for inertia. So the mass of an object, as we said, is a measure of its inertia, or its ability to resist any change to its motion. So, the greater the mass, the smaller the acceleration which results. So if you push your hardest against a small car, which has a small mass, you will have a greater effect than if you push against a more massive car. Remember, the resultant force acting on an object is the vector sum of all the forces acting on the object. The acceleration is always produced in the same direction as the resultant force, and this law of motion can only apply to objects with a constant mass. So this equation can be applied to any situation where there is a resultant force acting on an object of constant mass. So for a given object, the acceleration is directly proportional to the force. Now, if the net force acting on an object is non-zero, but in the opposite direction to the motion, the object will decelerate. So for a constant force, the acceleration is inversely proportional to the mass. Now, in this case, if the net force acting on an object is zero, according to Newton's second law, the acceleration of the object will also be zero. So in this case, the object will either be at rest or continue moving at a constant velocity, following Newton's first law of motion. So if we've learnt in today's lesson, we should have knowledge and applications of the laws of motions in appropriate situations, and we use F equals ma for situations where the mass is constant. So if we've been successful and we've learnt in today's lesson, we should be able to define and describe Newton's first law of motion, define and describe Newton's second law of motion, and understand how to calculate values based on Newton's second law of motion. So thank you very much for watching this video in the Forces of Motion module for OCR A-Level Physics, in the Newton's laws and momentum section, and on the topic of Newton's first and second laws. Thank you so much and have a lovely day.